Hello again, guys. I hope you're doing great. Welcome to another episode about flying physics. Today we'll deal with the forces acting on an airplane. During flight, the forces acting on an airplane are lift, drag, and weight, plus in power flight, the thrust. Let's examine all of them one by one. So, the first force acting on the airplane is its weight, and it acts on the center of gravity of the airplane and points towards the center of the Earth. The weight of the airplane is its mass multiplied by the acceleration of gravity. But the weight of the airplane during the flight is decreasing. Why is decreasing? Because the airplane burns fuel in order to move. So, it starts with an initial weight at the zero time moment, and is decreasing because the fuel is burned. So, it loses a mass of fuel every second, in the unit of time. This is called fuel flow. It is the mass of the fuel burned, the unit of time. So this is the rate of the decreasing mass of the airplane. And we can see from here that the mass of the fuel that is burned, which is the decreasing mass of the airplane, it's the fuel flow multiplied by the time. So this will be the mass of the fuel burned multiplied by the acceleration of gravity, which is the initial, let's say, m0 weight of the airplane, so the weight of the airplane is the initial mass minus the mass of the fuel burned multiplied by the acceleration of gravity. The second force acting on the airplane is the thrust. The thrust is the force that moves the airplane forward and gives its energy in order to climb, to descend, and in general to move. So, thrust. In general, thrust is produced by the change in velocity that the engine creates to the airflow and the change in pressure that the engine creates to the airflow just before and after the engine. So, thrusting comprises of two factors. First of all, it is the mass flow that entering the engine multiplied by the change in velocity that the engine creates to the mass flow, plus the area of the exhaust surface multiplied by the change in pressure that creates the engine. So, this is the airflow entering the engine multiplied by the exit velocity minus the inlet velocity plus I'll make a sketch here. The air entering the engine with a velocity vi and exiting the engine with a greater velocity ve. The pressure at the inlet is pi and at the exit is pe, and the surface, the area of the surface here we'll call it AI, and the area of the surface here AE. So now it's more obvious that the thrust depends on the change of the velocity the engine creates and the change in pressure that the engine creates. But usually the second term is more or less more smaller than the first term. So just because the first term is much greater than the second, we can omit sometimes. So finally we can say that the thrust of an engine is the mass flow multiplied by the change in speed that the engine creates. Of course, the mass flow is the density of the air multiplied by the inlet velocity, multiplied by the area of the surface from the inlet. Finally, we can see that the thrust is a function of air density, the aircraft velocity, and of course the change in the speed of the airflow that the engine creates. So we could say that this is a function of RPM. So the next force acting on the airplane is lift. Lift is the force that makes the aircraft fly. And we can calculate it from this formula, where R is the air density, V is the true airspeed of the aircraft, CL is the coefficient of lift, and S is the area, the surface of the wing. So this is the dynamic pressure, or the indicated airspeed of the aircraft, and the symbol is Q. Of course, as we can see, this is the true airspeed of the aircraft, and all the dynamic pressure is, as I said, the indicated airspeed of the aircraft. The coefficient of lift depends on the shape of the wing and the angle of attack. The problem is that for the airplane, in order to fly, we need the lift to be at least equal to the weight. So, in order to increase lift to become equal to weight, at least equal to weight, we need speed. So, who creates the speed? The speed is created by the thrust, and the thrust is created by the fuel. So, we need fuel in order to create thrust, in order to create velocity, in order to create lift, and the lift become greater than the weight in order for the aircraft to start climbing. Of course, we have also drag due to the motion of the airplane into the air, so an amount of thrust of the energy given to the airplane is consumed due to the drag, to the force of drag. Finally, on the aircraft acts the force of drag. Drag is the component of the aerodynamic force, or total reaction parallel to the relative airflow, and is the force, we can say that is the resistance due to the aircraft's motion into the air. The drag, which is consists of the parasite drag and the induced drag, as we already know. Parasite drag is the dynamic pressure plus the coefficient of drag, of parasite drag, and the induced drag, which is the indicated airspeed, the dynamic pressure, plus the coefficient of induced drag as the surface of the wing. So what we have now is that the coefficient of induced drag is equal to the square coefficient of lift divided by P and the aspect ratio of the wing plus another factor that we don't care about now. So if we substitute the coefficient of induced drag here, we are going to have next formula. And if we remember that the coefficient of lift is from this formula, when the aircraft flies in a straight level flight, the lift is always equal to weight. So if we solve for the coefficient of lift from here, we are going to have that coefficient of lift is that. And now if we substitute that the coefficient of lift in the initial equation, we are going to have that the drag is and finally we have what does this mean now? Let me clean the place here. What does this mean? This means that the drag is proportional to the dynamic pressure to square velocity plus inversely proportional to the true airspeed of the airplane, which means that is a function of squared velocity and also a function of inverse squared velocity. So if we are going to make a graph about this, we can clearly see that the first factor, which is the parasite drag, it increases with velocity, but the induced drag is decreasing with velocity, and we can sketch this, we can design that. This is the induced drag and this is the parasite drag. So if we add these two curves, we'll take the curve of the total drag. And we can clearly see that the total drag is minimum in a certain velocity that we call it minimum drag speed. Finally, when the aircraft is on the ground, we have, of course, the force of friction with the ground. Which is the coefficient of friction multiplied by the vertical reaction from the ground, which is the aircraft weight minus the aircraft lift. Why? Because let's say that this body is the aircraft, so we have its weight, vertical reaction from the ground, and the lift, which is being generated slowly as the aircraft is about to take off, or it's reduced when the aircraft lands and the lift is destroyed. So from this, from the first law of Newton, we have an equilibrium in the vertical axis. So the lift plus vertical reaction is equal to the weight. Therefore, vertical reaction is weight minus lift.